Okay, a common question when you're studying fields is asking, well, where does this pertain in real life? Well, one of the big things to understand is that when you're talking about potential differences, we're looking at charges moving. And that's very important when we start looking at circuits and that sort of thing. Electrical fields in and of themselves, they build a backbone behind what we have with current electricity, but at the same time, we've been studying, for the most part, static situations, okay, electrostatics. And one of the aspects that we're going to look at before we get into actual circuits is something that engineers and physicists like to use a lot, which are called capacitors. Capacitors are something that have the ability to store charge, given a certain potential difference between the plates that create this capacitor. So now let's just try to get a feel for what a capacitor is. All right, so now let's just say that I have two plates, okay, and separated by some distance here, filled with air right now, okay, and I take a little tiny charge right here. Okay, now there are electrons. Both plates are neutrally charged right now. I take an electron, okay, a little tiny electron, and I move it from this plate over to here, over to that plate. So now this plate has the electron. Okay, that would make this plate, because it's missing an electron, positively charged. This plate has an extra electron. It's negatively charged. And what happens in between there, okay, is that we have an electric field is set up. So we have an electric field, because now this is positively charged, this is negatively charged. We have an electric field that's set up between these two plates that goes in this direction. Okay? And whenever you have that electric field set up between two plates, it's pretty much a constant electric field, okay, we have a potential difference. So now, this has a charge positive E. This is a charge negative E. Okay? And there's a potential difference between the two of them of delta V. Okay? Now, by the way, in reality, we're not going to through this gap, we're not going to move the electron from one plate to the other, but it helps our understanding for right now. We're actually going to go around the back way and put the electron in going around the other way. Now, let's say same plates. Okay, we put it back to normal. Okay, put it back to neutrally charged. There's no delta V. There's no charge on the plates. But now, instead of taking one electron, okay, one electron here, okay, I take two electrons. Okay, electron goes over here, electron goes over here. Now, this plate would have a charge of positive 2e. This would have a charge of negative 2e. Okay? Again, the electric field is set up between the two of them. Okay? Now it's going to be a little bit stronger. Okay? Now we have a stronger field because I have more charge set up between the two plates. Additionally, because the electric field is bigger, okay, my potential difference between the plates is going to be bigger. Now it turns out that if I double the amount of charge between here and here, I also have twice the potential difference. And that's very important, okay? Because if I go on and I put on like realistic numbers of electrons between the two of them, it's very hard to move one electron at a time, okay? But let's just say that I take approximately 10 to the 13th electrons, okay? It gives me about 1.6 microcoulombs on this plate. And I move all those electrons over to the other side. So now this is going to have, so I move all of them over there between the two sides. So now I have a charge over here of 10 to the 13th electrons, or elemental charges, positive. Over here I'd have negative 10 to the 13th, a charge of negative 10 to the 13th elemental charges. I set up a much stronger and realistically measurable electric field between the two. It doesn't really create much of an electric field between these two. Okay? And from that, okay, here, one electron gave me delta V. Two electrons gave me twice that delta V. So now if I do it again, my delta V here is going to be 10 to the 13th, whatever this delta V was. Okay? The key is that charge to potential difference ratio remains constant, okay, given this arrangement of plates. Okay? It's not constant in all cases, okay, but it's constant for this particular set of plates. Okay? Each plate's going to have its own constant. And we call that constant, that ratio, okay, of Q to delta V, we call that the capacitance. And for historical purposes, we pretty much drop the delta V and we just call it V. So that ratio of charge to potential difference is equal to the capacitance, C. Okay? I'll write it out, capacitance, and it's C. Okay? Now, C, as we say up here, is equal to Q over V. We want to take a look at units real quick. So the units of capacitance, this is going to be coulombs per volt. Okay? And this is a very common unit. And we call that the farad, after Michael Faraday. Maybe like, I don't know why they cut it off at the farad instead of the Faraday. It'd be like calling it a sween instead of a Sweeney, but what have you, okay? So now, the farad is capital letter F, and that's the way that we're going to be talking about it now. All right. So now, one important thing to note, okay? This capacitance, it doesn't matter what the electric field is, what the potential difference is, how much charge is on it, okay? This capacitance is a property of the device itself. Can't say it's a property of the material, okay? But it's a property of the device itself, okay? It has no dependence on anything electrical whatsoever, okay? Something has capacitance because of its very existence. It doesn't have capacitance because of the electric field or because of charge on it or because of delta V across it, okay? It has capacitance because it exists. So now, let's take a look at a few hopefully relatively simple examples. So now, first thing that we want to take a look at is how we're going to get these charges from here over to here. Okay? They don't actually jump that gap, by the way. They can, and that's when you break a capacitor typically. You get an electric spark that jumps the gap between the two of them, and basically, typically you're going to ruin your capacitor when you do it, especially if you have a dielectric in the middle there. But typically, and the way that we want a capacitor to charge up, okay, is to connect it to a battery. So I connect this to some sort of battery. This is why we have to introduce some circuit elements here. This is a battery. Okay, it has a positive end. So by tradition, this is going to be the long plate up here will be the positive. The short plate right here is going to be the negative. Sometimes I'll just draw it like this because it's faster. Either one counts as a battery. A capacitor, okay, we symbolize with two plates, okay? And that's the simplest form of a capacitor, where it's just the two plates that exist between them, okay? And we also have and we can rotate these, and this could be arranged horizontally or even at an angle or anything like that. But typically, they're going to be either vertical or horizontal. Be careful how you draw these. Notice, especially if you only use the two lines here. The only difference between a capacitor and a battery here, the battery has the long and the short, and the capacitor has the two long lines. You got to be careful when you do that. The only other circuit element that we're going to introduce really in this chapter, okay, is a switch. Okay, so this is a capacitor, and this is a switch. Okay. So now, if I make a loop of wire, and all I have on it here is a capacitor, there's nothing that I can do to charge that capacitor, okay, unless it's already charged. The electrons aren't going to jump from here to here, okay? And realistically, I need some sort of electric field inside here to drive the electrons from one plate to the other, okay? And right now, in that circuit, I have nothing, okay? I need to introduce the battery to it, okay? So if I put in a battery, and again, I'm going to emphasize that the long plate is the positive, the short plate is the negative. I won't always put that positive and negative in. After a couple of weeks, I probably won't put it in at all, except for points of emphasis. Okay? So now, what's going to happen here? Okay, I have this battery. This battery has a potential V. It's really a potential difference, but we've come to call it just V at this point. What's going to happen? Okay, it has a positive end. What's attracted to a positive end? Electrons. Okay, and as we know, electrons are what flow through each circuit. Okay, if protons start moving and we have a metal, then we've got issues. Okay, and over the negative end, okay, this negative end is going to repel electrons. So those electrons are going to come out of the battery and go up to this plate over here. Well, when this plate has a deficit of electrons, it acquires a positive charge. When this plate now has an excess of electrons, it has a negative charge. Okay? Now, what happens is that we get this, this drive of electrons. So now, as this gets charged up, okay, a potential difference exists across the two plates. Ideally, okay, with perfect wires, this would charge up instantaneously. Realistically, with the very small amount of resistance of wires, okay, it does take a non-zero amount of time to charge up. With wires, it's going to be a very small amount of time. With if we put a resistor in there, it takes a little bit longer. Okay. Now, what happens is around any loop, okay, we need the voltage to equal 0. So now I go across the battery like this. Okay, I'm going to go around in a circle like this. I go across the battery, and I gain voltage here. So what that means is I have to lose that same amount of voltage over here. So the voltage of the battery here, called VBAT, has to equal the voltage of the capacitor. Okay, so voltage of the battery will equal voltage of the capacitor. And we have a certain amount of charge here. Okay? And the amount of charge that builds up depends on the capacitor. Okay? And as we pointed out before, Q will equal capacitance times the voltage. So now, I know what the voltage of the battery is. I know what the capacitance of our capacitor is. And I can figure out the amount of charge that's going to build up on these two plates. Okay? Now, the final thing here, so I've got that same V over there. Final thing here before we move on and start doing calculating the capacitance of a capacitor. The amount of charge that builds up. Okay. Quick question: what is the net charge on this whole capacitor? pause it for a second. Okay? I want to know what the net charge on this capacitor is. Well, if I have a positive charge up here and a negative charge down here, and they are equal, okay? The amount of charge up here and the amount of charge here are equal, they're just opposite charges. So if it's equal and opposite, the net charge on the capacitor itself is 0, okay? The total charge on the entire capacitor is 0. But that wouldn't be very interesting or very useful in our calculations. A positive charge Q will develop on one plate, a negative charge Q develops on the other plate. When we describe the charge on the capacitor, we say that the charge is just equal to Q, okay? Not worrying about the fact that one of them is positive and one of them is negative, and they are equal and opposite. But we say that the charge on it itself is Q. We don't call it 2Q or anything fancy like that. We just say that it's Q. All right, let's take a look at pretty much the last thing of relatively hard integrations before the end of the year. There's a couple other things that we're going to have to look at with integration. We're going to have to look at differential equations as well. But as far as pure integration, this is going to be the last of really the hard stuff. And realistically, it's not as hard as, definitely not as hard as some of the other things that you've done. Okay? So now, let's take a look at a parallel plate capacitor. Now, capacitors are made of conductors. Okay? They have to be conductors because if they were conductors, then you couldn't have the charges flow out of them. And if the charges didn't flow out of them, you wouldn't have any charge buildup. Okay? So now, let's just say that I have this capacitor that's charging up. I'm going to have one plate here be positively charged, and I'll have another plate here that's negatively charged. And we want to figure out what the capacitance of this is. Well, in order to do that, we have to look at the ratio of the charge to the potential difference. Okay? Well, now, we're going to set up Gaussian surface. Okay? We're going to assume that the electric field is all contained within the capacitor. Now, in reality, there's a little bit of what are called, the edge effects that come around the outside. We neglect them. Okay? They are much weaker, orders of magnitude less than what's on the inside. Okay? So it's only on the inside that counts. Right? So we're going to set up our Gaussian surface here. And this is not an infinite plate. Okay? So we're going to look at the total charge on the capacitor. Our Gaussian surface completely has that top plate. Okay? We're not assuming an infinite plate here. And we're assuming that there's nothing on the outside, none of those edge effects, so we don't have to worry about anything out over here. Okay? So now, let's take a look at the electric field. If I do Gauss's law, okay, I'm going to say Q enclosed is equal to epsilon naught integral of E dot dA. Now, Q enclosed, usually we've been calling that sigma A. Okay? Well, in this case, we're not looking at an infinite plate. Okay? We're looking at something with charge Q on it. So that Q enclosed is just going to be Q because we have the entire plate. Epsilon naught. Now, we're assuming that the electric field, okay, is only within this area. Okay, again, we're neglecting this stuff out over here. And it's fine. Okay, again, it's much weaker. So we call that E, and we're going to say that it's the area of the plates itself. Okay? So now, the electric field, so now this will be important as well, but the electric field is equal to the epsilon naught Q over A. Part of the reason why we use epsilon naught instead of K, okay? Because epsilon naught, when you're dealing with parallel plates, which is a very common arrangement, epsilon naught comes in very handy. Now, now we have to take a look at the, we have to look at the potential difference between the two plates, okay? And we know that the potential, and instead of calling it delta V, we're just going to call it V, okay, is equal to negative integral of E dot ds. Okay? And we're going to go from the negative plate to the positive. So my path of integration in this case, okay, and I know this will come out a little bit weaker. So you'll see it. So here that would work. Okay. My path of integration is going to be from the negative plate, and it's not actually going in curved direction like that. I'm just trying to emphasize that that's our path of integration. Okay. So this is our path of integration. Now, I'm going to go from the negative to the positive. Something to point out here, okay? E dotted with ds. Okay? Oh, and so our path of integration, that's s. So ds is a little small part of that. E points in this direction. The path of integration goes the opposite direction. So now, that angle between them is 180 degrees, which means that the dot product will give you a negative 1. So this becomes, instead of E ds, it becomes negative E ds. So now, when I plug that negative in up here, I get the integral from negative to positive of E ds. Okay? That's where the negative drops off. Now, I know that the electric field is constant in there, so my voltage here is epsilon naught Q over A. That's what E is. I integrate. Now, from negative to positive, I'm going to say that the distance between these two plates, and I should have mentioned that earlier, is a distance d. So I'm going to go from 0 to d over ds. Well, that's going to make my voltage here equal to epsilon naught Q d over A. Okay. Now, my charge here is epsilon naught EA. So if I do my capacitance, which is equal to Q over V, Q is equal to epsilon naught E times A. My potential is equal to epsilon naught okay, I'll do it this way. Sorry about that. Erase that part off. Okay, Q, I already have Q in there, so I think it'll cancel out. Over V, which is epsilon naught Q d over A. Right? First of all, the Q's will drop out. Okay? And I don't want an improper fraction. Okay? So I wind up with epsilon naught, multiply top and bottom by A, epsilon naught A over D. And usually I'll call it a little parallel sign here. The capacitance of a parallel plate capacitor is epsilon naught A over D. Okay? Notice, epsilon naught is a constant. A is just the area of the plates. D is the distance between them. Again, no electric field, no potential difference, no charge. Okay? It's just, it has capacitance because of its existence. Right? It's just a property of the materials. It's just the geometry of the materials. It has nothing to do with the electric field. It is a separate property. Okay? It affects electrical properties, but in and of itself, it is not affected by electric circuits or currents or anything else like that. All right? Now, we're going to take a look at a couple other ones. Okay? We're going to look at a cylinder and a spherical capacitor. I'm going to go through these pretty quickly. The integration gets a little tougher. But in reality, knowing how to do this, this is probably where you would take a look at it on an AP exam. Okay? So let's just say I have a capacitor. But I do want to go over this so you can at least see it. You don't think that I'm pulling numbers out of thin air. So now, a capacitor is not an infinite thing. Okay? So we can't say that goes on forever. Right? And we're going to have some sort of thing in the middle here. So it's going to have, essentially it's like a coaxial cable. Okay? This will definitely have a thickness to it. This as well has a thickness on the side. Okay? So this has, comes around it as well. So it's a cylinder that looks like that. Now, the only reason why I even draw that, okay, instead of just the cross section, I want you to understand that the what we have is not an infinitely long cylinder. Okay, so when we take a Gaussian surface here, okay, so I'm going to do a Gaussian surface right like this. And yes, I know the drawing is a little messy. Okay, it has a definite beginning and a definite end. Okay, so we have to take into account not only the radius, but we have to take into account the length. And but again, the electric field that exists here is going to be, we don't worry about what happens out here at the ends. Okay? We only care about what happens in the middle, because what happens in the middle is much stronger than what happens on the outside. Again, orders of magnitude greater. So now, let's take a look at this from a cross section. From a cross section, I'm going to have something, okay, like this, right? Where I'm going to say that on the inside, it's going to have a positive charge. Around that, okay, I'm going to have another material, or another sheath around this, okay? And this is going to be negatively charged. This will have, I'm going to say that this is a radius A. Okay, to the inner wall here will be a radius B. And I'm going to set up a Gaussian surface, and just to help you see this a little bit more, I'm going to fill this in a little bit. I don't want to fill it in too much so you can't see what's going on. All right? And I'm going to create a Gaussian surface around here. Okay? It goes like this. So that's my Gaussian surface. And this is going to have some radius R. Now, and again, this will go into the surface. It has a length to it. Okay, it has. It's going to be the length, run the length of our capacitor. Okay. Again, this will have charge positive Q. This will have charge negative Q. And again, we're going to integrate instead of going from inside to outside. We're going to integrate the other way. Okay. This is going to be my path of integration S. So let's take a look at the electric field, and then take a look at the potential difference between the inner and the outer surfaces. And that way we can get our charge on. All right, following that path of integration, I've got, well, first doing the Gauss's law. Okay, Q enclosed equals epsilon naught integral of E dot U. Okay. Now, again, I don't care about the end caps. The end caps are going to have very little flux It's not zero, but it's not going to have much. Okay? The electric field is going to be much smaller on these entries. So really, I'm only concerned with Q enclosed, which is just Q, equals epsilon naught. Okay? Now, the electric field is not constant all the way through here, but around this Gaussian surface, the electric field is going to be constant. So that's going to be E. My dA is going to be the area of this, which will be 2 pi L times R. Okay? This is the surface area of that cylinder. Again, yes, you do have plus 2 pi r squared, but the end caps do not contribute an awful lot to the electric field. Okay? So now, my electric field here will equal 1 over 2 pi epsilon naught Q over L R. Okay? Again, this is a pure constant, so I try to separate it. Then I put some of the properties off to another one. Just helps identify some things a little bit more easily. All right. Your potential difference here, B. Again, it is a potential difference, but we just call it B for tradition's sake. And I'm going to integrate here from negative to positive. All right, now we have to be very careful here. Signs matter, and it gets a little crazy. Again, the electric field, okay? The electric field is going to point from positive to negative. So my electric field goes out like this. Okay? So now if I take away the Gaussian surface, only because I've already used it, I'll use the red. My electric field is going to point like this. Now, my path of integration goes back the other way. So again, I would say E dot ds is equal to negative E ds. E is not a constant, so we have to definitely integrate this. Okay. Now, here's where it gets a little funny. We're going to integrate with respect to R. Okay, we have to integrate with respect to R. It's one thing that changes. The length isn't changing, Q isn't changing. R is a variable. Okay? So we're going to integrate with respect to R. But my path of integration goes this way. R points out. So what happens is ds is equal to negative dr. So negative E ds is equal to E dr. All right, so we've done our final substitution here. I know that gets a little funny. Those of you in Calc 8B or Fun Calc, try to follow along. BC kids, you should follow what I just did. Okay, it's just that I made a substitution in for so I can get it in terms of dr because this is r, and this goes in this direction. Okay, S goes in this direction, R goes the other direction. So the signs have to flip. So now what I have here is that my voltage will equal negative, integral from negative to positive of, so I've got negative EDS, so I've got E dr. So now I plug in, my voltage will equal negative, integral from negative to positive. My negative here, radius is B, and I integrate towards A. E is going to equal 1 over 2 pi epsilon naught, I'm going to be able to pull all that out, Q over L times R times dr. Now, Q is constant, L is constant. The only thing that I'm integrating is dr over R. So what I have here, negative integral B, put it here, Q over 2 pi epsilon naught L. Yes, I know I usually separate, but I'm trying to save some space here. Integral from B to A of dr over R. Now, at this point, whether you're in BC or AB, even fun calc at this point, should understand, because I've done it a few times, that the integral of dr over R is going to give you the natural log of R. So now, this would equal negative Q over 2 pi epsilon naught L. Natural log from A to B, so it's going to be the natural log of A minus the natural log of B. Now, hopefully that should fit, hopefully. No, I'm just going to rewrite it down here, just in case it doesn't fit. So now my potential would equal negative Q over 2 pi epsilon naught L. Natural log, it's going to be top minus the bottom, ln of A minus the ln of B. Okay. Now, I've got a negative here that's going to flip the order here. So I wind up with my potential equal Q over 2 pi epsilon naught L. Natural log of B minus natural log of A. So rewriting that, I wind up with, natural log of B minus natural log of A. Okay, from your natural log properties, you're going to get a potential of, I'm just going to put it here, potential of Q over 2 pi epsilon naught L. Natural log of B over A. Now, capacitance will equal Q over V. So this is going to be Q divided by Q over 2 pi epsilon naught L. Natural log of V over A. And Q's will drop. Capacitance is equal to 2 pi epsilon naught L over natural log of B over A. Okay. So now, again, take a look. 2 pi epsilon naught, all constants. L is the length of it. B is the outer radius. A is the inner radius. Okay? Everything is just a property of the device. It's just the geometry. No charge, no voltage, no electric field. That determines what the capacitance of this cylindrical capacitor is. Okay. One final thing that we're going to do is spherical, and I will try to run through this relatively quickly. We've already have the setup for it. It's not going to look like this. It's just going to look more like that in and of itself. But give you a chance to write everything down. And this is something I'm more doing to kind of, and I'm definitely putting it on here because I kind of want to get it out of the way. I want you to understand it, and I want you to understand where the capacitance comes from. But it's going to be using the capacitors where we're really going to do a lot of work. Okay? Your homework in this is, there's only 6 problems that you're going to do. And it's the first 6 problems in the chapter that cover this material. And you use what the capacitance is. You don't have to prove it now. Okay? So let's just get this one out of the way for the spherical capacitor. And then we move on and make use of the capacitors here. All right, now for a spherical capacitor, instead of this being a cross-section going along, this is just looking at a 2-dimensional representation of a sphere. Okay. Now, again, the inside is going to be positively charged. The outside is going to be negatively charged. Okay. Inner radius is A, outer radius B. The electric field, again, points out our path of integration is still going to be inward. So let's take a look. I'm not even gonna, if I do my Gaussian surface here, okay, if I do it right here on the inside, okay, it's the electric field from, it's just the charge enclosed here. Charge enclosed does not include the negative. So now all I have is that the electric field is equal to 1 over 4 pi epsilon naught Q over R squared. Okay, done. You guys already know this. I'm not going to go through the Gauss's law on that. Again, you know how to do that. Okay. My voltage, on the other hand, is a little bit more complicated. Voltage is going to equal, again, the integral from the negative to the positive of E dot ds. And it's important to see this again. It helps you see how the integration works and you get a little bit more comfortable with it. Okay. Now, again, E points out. My path of integration points in. So E dot ds, okay, because the angle between them is 180 degrees, again, will be negative E ds. Okay? So the negative goes away from the up front here. So my potential is equal to the integral from negative to positive of the electric field, which is 1 over 4 pi epsilon naught, Q over R squared. Okay, and again, I wind up with having to do dr. So dr, now remember, dr is equal to negative ds. So I have to put a negative out front here, and there you go. Okay, so now again, q is constant, 4 pi epsilon naught is constant. So I have my negative q over 4 pi epsilon naught integral from b to a of dr over r squared. So now, dr over r squared, okay, that's r to the negative 2. So I wind up with, well, negative q over 4 pi epsilon naught. Okay, it's going to be times a negative 1 over r, and that'll be integrated from b to a. The negatives will go away, positive, positive. So I wind up with my potential difference here equaling q over 4 pi epsilon naught, 1 over a minus 1 over b. A is smaller, which makes this number bigger than this number. So you still wind up with a positive, which is good. So now my capacitance, again, is just Q over V. So now my capacitance will equal, now we can, well, let's see what I have now. Q over 4 pi epsilon naught, 1 over A minus 1 over B. Q's drop, okay? So I rearrange, I wind up with 4 pi epsilon naught times 1 over A, divided by 1 over A minus 1 over B. Mathematicians, physicists, somewhat, but mathematicians especially don't like improper fractions. So we multiply everything by AB, top and bottom by AB. Okay? So I do AB up here times AB down here. Okay, so my capacitance is equal to 4 pi epsilon naught AB over, if I multiply this by A times B, I wind up with B. Multiply this by A times B, I wind up with A. So the capacitance of a sphere is equal to 4 pi epsilon naught A over 4 pi epsilon naught